Right. So the chain rule tells you that if there are these three things that are related to each, three variables related to each other, z, x, and y, you can say z is a function of x and y. So then del z del x at constant y times del x del y at constant z times del y del x at constant z. I hope I'm saying the right thing. Is equal to -1. So it's a cycle. Z, x, x, y, y, and z. That is. Right. So that is equal to -1, and that can be derived very easily. So what it says is del z del x constant y del x del y constant z del y del z constant x is equal to -1. Okay, and this you can derive very easily by just saying that z is a function of x and y. If z is a function of x and y, then the change in z dz is simply the change along the x direction plus the change along the y direction. So del z del x, that's the slope along the x direction, times whatever the change is in x, plus del z del y, the slope along the y direction, times the change dy. That's all. Now, I can do a lot of maths on this. Right. What I want to get, just one moment, let me complete this. What I want to get is del z del x at constant y. That term is here, right? This term, it's here. What I wish to get is del x by del y at constant z, which is missing, right? Del y by del z at constant x is here, 1 by that, right? So what I need is del x by del y at constant z. So if I do that, if I do a divide by dy everywhere at constant z, then what I get is del z del y at constant z, which will go to 0 because I'm trying to change z, but I'm holding the condition that z is constant, is equal to del z del x at constant y del x del y at constant z plus del z del y x del y at constant z, right? So if that is the case, then all I know is that this fellow goes to 0 and this fellow goes to 1, and then I just rearrange. I rearrange and I get back the cyclic rule. Yes.
That was just differential. It wasn't partial differential.
Yes.
Can we do that?
So what is the meaning of partial differential? All I am saying is that this is dz. This is the total change in z, right? And z is a function of x and y. Right? And now I say, okay, let me change z with respect to some function, holding all others constant. That's what I am doing. Right? Yes, very much. Very much. It's perfect. No problems in this one. Good. That's a very valid question. I can only write this when it is a state function. I cannot write this expression of dz is equal to a change in x times x dx plus a change in y times dy if it is inexact. Because an inexact function, actually, a path function is not a function of variables, right? It's a function of the path. Here we are just associating z with the two variables x and y. So it's legal only to write when this is a state function. So good. So this necessarily is true when z is a function of x and y. When we write z as a function of x and y, automatically it means it's a straight function, right? If it's a path function, then I cannot write it that way. So state functions only true for state functions. Good question. Yeah. Somebody was ready.
So why in the first equation that is -1 instead of 1?
That's what it will come out. Now if I do that, this fellow would go on the other side, become a minus, right? So that would be -1 times del x by del z by del y at constant x, and then I just do a division by that.
Second equation, so you have just added change with respect to x into dx and change with respect to y.
That is the total change in dz is the change along the x direction plus the change along the y direction.
That should be possible only when z is equal to x or y or some condition is there.
Z is equal to
X into y or something like that.
x into y. On the other hand, the condition is that you can independently vary z. Right? Yeah, what we are dealing with is independent variables. Right? See, the first term does not depend on the second term. I can independently vary z along the x direction. I can independently vary z along the y direction. If that cannot happen, if for somehow x and y are correlated, right, they are not independent, then it will be difficult to write such a thing.
So you said that if z is a function of x and y, then it's a state function.
Yes.
But in case of v, sir, like we write v minus v dot.
Yes. Very much.
Sir, it's also a function of
No? No? See, that's a very special case which you take. Once you define the path, then it becomes a function. Because then the path is known. Till you do not know the path, when I say it's a function, it just depends on the value of x and y. Right? A path function is not that way. It does not depend on the value of x and y. Depends on how x and y have been changed. Right? If I am writing z as a function of x comma y, all it means is that I can define z for any value of x and y. I cannot do that for a path function. Remember this. Although we call it a path function, still in the true sense it's not a function, right? We have to define a few more things. Okay. Okay, so let's go ahead with things that you'll need now. Okay. So where were we last time? We had just talked about the Joule-Thomson experiment, right? Okay. Now let's try to do some maths and show you guys one of the very important results, that Cp minus Cv is equal to R. So in most of my lectures I am ignoring n, the number of moles, right? As long as we are in a single component system, I am ignoring it. So don't get confused by that fact. So I should actually be, if I have to be very cautious, I should write Cp molar minus Cv molar is equal to R. Okay, so what we want to prove it, Cp minus Cv is equal to R, and that's true only for ideal gases. So now we go back to the definitions. The definition of Cp, del H by del T at constant pressure, right? And what is the definition of H? U plus PV, right? So I could write, let's do it over here, dH is equal to du plus PdV plus VdP, but we are dealing with constant pressure, so VdP term goes away. So all I'm left with is PdV. And from here, if I do a del H by del T at constant pressure is equal to del U by del T at constant pressure plus P, which is a constant, times del V by del T at constant pressure, and del V by del T at, so our ideal gas equation is PV is equal to RT, right? Very ideally it should be V molar, right? But we are just ignoring that for the time being, as I said earlier, so just for 1 mole. From there what I get, del V by del T would be equal to R by T, right? So what I would get then is simply del H del T at constant P is equal to del U del T at constant P plus R. The left side I know is Cp, the right side is something plus R, right? And since I know the relation that Cp is equal to Cv plus R, this fellow should be Cv. It is Cv, but you know, you can't assume that, right? So what I'll go back is to the definition of du, which we already know. Du is equal to Cv dt plus pi t dv, right? And I already know. Now let's do it. Let's do a, what I need is du dt at, or del u del t at constant pressure. So I just divide by dt and write the conditions of constant pressure. So what it gives me is del u del t at constant pressure. Anyway, this fellow is 0, right? For ideal, we are working with ideal gases for the moment. So that fellow is 0, is equal to Cv. Right? For ideal gases at constant pressure as well. See, this is the total expression of du. I don't have any conditions of constant volume or pressure for the moment. Yes? For an ideal gas, if there is no change in temperature, there is no change in internal energy. This is something we already know. Right? Now what I say is, okay, I want to see what is the change of internal energy with respect to temperature held at constant pressure. Right? And that comes out to be nothing but Cv. And that gives you, if I plug this back into the equation, then this fellow comes out to be Cv, right? So this gives me the expression that Cp is equal to Cv plus R, which is what we were looking for. Any doubts with this? That's fine. Great. So now that we've already proven that Cp is equal to Cv plus R, we can go on to study more kinds of expansion and the next one that I'm going to take up is the adiabatic expansion. Right. And then we can see a few thermodynamic cycles, how it changes, how can we evaluate thermodynamic quantities if I give you some cycles. We could practice a couple of cycles today. Okay. So adiabatic expansion. Yeah, we are always worried about expansions, huh? Not compressions. I guess that gives us energy. Okay. No, compressions are important. We will come to see some of the compressions when we start with the second law. But for the moment, let's say adiabatic expansion. So what we have is a container, the usual thing. P1, V1, temperature is 1, external pressure is P1, so it's in equilibrium with outside. And let's do it reversibly to start with. So P external is equal to P2, P2, V2, T2. Right? So in the isothermal case, temperature was constant. Here it's not. I mean, we don't assume it to be constant. If it happens to be constant in a special case or something, we'll see it later. So what is the information that I have to start with? We'll do it for ideal gases. The more complex equations are meant for your people to use. Okay. So what is the information that we have? First, adiabatic. Let's convert the English into mathematical terms, right? Q is 0 or dq is 0. Okay. What else? Reversible, somebody said. Great, reversible. dw is equal to minus p dv. Great. What else? Piece of information that we have.
Initial and final states. Initial and final states.
That's P1, V1, T1. That's what we want to calculate. We want to relate. Ideal gas equation. Great. That gives us the information that du is Cv times dt. Right? What else do we know? That's the information that we have from the system. Now we can apply the first law. And if we apply the first law, du is equal to dq plus dw, then what we get is Cv times dt is equal to minus p of dv. It's ideal gas, so there's another equation that we know. PV is equal to RT. Again, 1 mole. Now, why I'm not emphasizing on the mole is because all the systems that we are studying are closed systems. So the number of moles are always conserved. Okay. So later on, if I want to add the number of moles, I can always just put that in term into the equation. Okay. So let's make these substitutions. Yeah. This holds true. This is an ideal gas. Right? What does not hold true is that this PV remains to be a same constant throughout the expansion. In case of an isothermal expansion, what you had was PV is equal to constant, right? And in case of adiabatic, you already know that PV to the power gamma is equal to a constant. These constants are not the same. This is what we are going to derive right now. You know that for the entire isothermal expansion, PV is a constant. But this equation, the ideal gas equation, always holds true. So one should not get confused between these two things. Okay, so getting back to Cv dt is equal to minus P dV and replacing minus P dV as equal to minus RT by V dV, right? And then I could take the temperature on the other side since we have terms of temperature on the left. So Cv dt by T is equal to minus R dV by V, which I can always write as Cv d log T is equal to minus R d log V. And then I'm going from T1 to T2 and the volume is going from V1 to V2. So all I need to do is, and I know my Cv, so Cv is constant over narrow range of temperature. That's what we assume. So Cv can come out of the integration, and then all I need to do is Cv integrate from T1 to T2 d log T, and this is equal to minus R integrate d log V from V1 to V2. Done. Integration finished. So which would be Cv log T2 minus log T1 is equal to minus R log V2 minus log V1, right? Which I could just write as Cv log of T2 by T1 is equal to R log V1 by V2, and then put it like take the Cv on the other side and then make the exponential, right? So make it exponential. So this is, or rather before that, T2 by T1 is equal to log of V1 by V2 to the power R by Cv, and then that gives me T2 by T1 is equal to V1 by V2 to the power R by Cv. And just a few minutes back we proved that R is equal to Cp minus Cv. So all I need to write over there then is T2 by T1 is equal to V1 by V2 to the power Cp by Cv minus 1. Yes. What this ratio Cp by Cv is also known as gamma. Right. So T2 by T1 is equal to V1 by V2 to the power gamma minus 1. One thing to be remembered is that if you take monatomic gases, then Cv is 3 by 3. Okay, how do we get that? We just use an equipartition principle. Everybody knows that. Okay, so half kT for each degree of freedom. So there's half kT for XYZ translation, that gives us 3 by 2 kT. There's no rotational degree of freedom, right? So 3 by 2 kT and Cp comes out to be plus R, that's 5 by 2 kT. So gamma is 5 by 3. So monoatomic gamma is equal to 5 by 3, and then it keeps increasing. For polyatomic cases, gamma comes out to be, right. So Cv is 3 times R, and Cp would be 4R, right. So for polyatomic, 4 by 3, and for diatomic it's somewhere in between. So, yeah. What's important is that this gamma is always greater than 1. Gamma greater than 1.
Sir, when do we consider the vibrational?
Okay, that's a very interesting question, and I think the complete answer can only be given by quantum mechanics, and I hope that will be done in the second half of this course. Right? First thing, okay. At lower temperatures, the vibrational motions are all frozen. So there's hardly any contribution. Right? Only at higher temperatures these get activated. And then there's a contribution due to potential energy and one contribution due to the kinetic energy, which you will definitely learn in your quantum mechanics course. So the contribution, if there is any at higher temperature, is not half kT but kT. I mean, I can only answer up to that for the time being, but in your quantum mechanics course, you get to know how. In fact, in the start itself, you will be taught about vibrational motions and Einstein's theory on vibration, on the heat capacities. From there, you'll get an idea, and then later on, I think that should be the second solution of quantum mechanics. The first one would be a particle in a box, and the second one would be a harmonic oscillator, where we will learn more about vibrations. Okay, good to ask that. Anyway. Okay, so here we are. Gamma is always greater than 1. And in a moment, I'll show you what's the consequence of that. I could use my ideal gas equation, come back to just replace this. What I want is essentially PV gamma as a constant. Right now what we have is TV to the power gamma minus 1 is a constant, right? This is giving me something like TV to the power gamma minus 1 is equal to a constant. Okay. Now I just replace temperature by pressure using PV is equal to RT. So that would give me P2 V2 by R, P1 V1 by R, so R and R cancel, is equal to V1 V2 to the power gamma minus 1. So what it gives me is, so V2 goes over here, V1 goes over here, minus 1 gets cancelled, so P2 by P1 is equal to V1 by V2 to the power gamma, or PV gamma is equal to constant. So these are things which you already know and you always need to know. Now, the fact that for an adiabatic expansion, PV to the power gamma is a constant, while for an isothermal expansion, PV is equal to constant. Right? If I give you one pressure, which volume would be higher? Right? So if I were to plot this, so always let's say I were to start with P1 and then I'm going to some value P2. So my starting point is V1, right? And isothermally I have gone from here to here. So that's my V2 isothermal, right? It's not a straight line. Excuse me for my drawing abilities. Well, it doesn't look straight anyway. So what we know is that since gamma is greater than 1, Pv to the power of gamma tells us that V adiabatic would be smaller than V isothermal. So that's my V2 adiabatic. So if I were to, so it does not matter about the constant is not the same, right? But if I were to end at the same pressure, V adiabatic would be smaller. Yes? Yes, no, maybe, okay. Another way of comparing this is not the same pressure but the same volume, which I could actually do on the same plot. Just a moment. So that would be the isothermal volume where, so if I were to expand it to the same volume, that green point would mark the same volume, right? If I were to expand it isothermally. And then what do I get out of it? Right? At a much lower pressure. What happened over here in the isothermal phase? The temperature was constant. So that's our isotherm. So let me draw it with green then. Maybe that's the adiabat. Right. So we've expanded the gas at constant temperature in case of the isotherm. In case of the adiabat, there's a change in temperature. Right. And since the volume of the gas is larger, we've expanded. Yes. What about the temperature? Don't use PV is equal to RT to compare the temperatures. Right? Because that is not the same, the temperature is not the same, the pressure is not the same. You can't use that equation. What you can use is PV to the power gamma minus 1 as a constant. Yes. So in case of an adiabat, T2 is less than T1, right? So the gas always cools down. No doubts. Everything is fine. Till now everything is fine. if I actually do this process irreversibly. So irreversible adiabatic expansion. What we've seen is for the reversible case. Let's keep this drawing over here, and we'll keep this thing very much in our head, what this thing looks like, and look at an irreversible expansion. So an irreversible expansion, a single step irreversible expansion, right? So to start with, I had P1, V1, T1, and the external pressure was P1. I immediately switched the pressure from P1 to P2, which is the final external pressure. So I don't do it reversibly, but I just do it in one shot. Right. So again, the information at hand. So the irreversible case now. So what's the information at hand? Okay, it's still adiabatic, so Q or dQ is 0. It's ideal gas, so du is still Cv dt, right? And Pv is equal to RT still holds true. Third one, work done is irreversible, so dW is minus P2 times dV, right? And the first law still holds true, so du is equal to minus P2 times dV. With all these equations that are there, we again get the same thing. Cv dt is equal to minus P2 dV. Now P2 is just a constant. It's just the external pressure, the final external pressure. Right. I integrate the thing. What I get is Cv P2 minus P1 is equal to P2 V2 minus V1 minus P2 V2 minus. Okay. Don't get much information out of this, so let's try to rearrange some things. I already know. I already have some information over here. PV is equal to RT. Let's put it over there. So what we have is so what I did was just to write V is equal to RT by P. Just did a bit of manipulations for this. Okay. What's important is that this P2, the final pressure, is lower than the initial pressure P1. Okay, which means that this term is less than 1, right? Which just tells me that T1 is higher than T2. So again, even in case of irreversible expansion, gas cools. Now the question is, does it cool more in case of the reversible expansion, or does it cool more in case of the irreversible expansion? More in reversible. and you could come back to yes, yes. So the final volume is the same. Yeah, the final pressure will not be the same. Ah. So this P2 which I have written over here is not the same P2 as in the case of the reversible. Good thing you pointed it out. Let's make sure and let's write it down over here. Not the same as in the reversible case. Just P2, right? V2 is the same. The final volume is the same. P2 is not the same. V2 is the same. This is a gas. It's an ideal gas, obeys the law. PV is equal to RT. So P2 will not be the same. Okay. Some way, some mathematical treatment that you can tell me that yes, the temperature in case of irreversible. So what we are asking is temperature 2 in case of reversible is less than temperature 2 in case of irreversible. Great. Work done is less. So in the irreversible case, now you have to be very careful over there. In the reversible case, you get maximum amount of work, right? But that work has a negative sign because it's going from the system to the surrounding. The work is being done by the system, so I always take care of the sign. Minus W reversible is greater than minus W irreversible. Okay. If you want, you could have used a modulus sign. Work done by the system reversibly is maximum. That's what I said. Yeah. If you come back from here, you will get that maximum amount of temperature change. Yeah, equate it back to du, like CVDT. Or bring it back to PdV, pressure into change in volume. Right? If I do that, what is the pressure change? Right? Okay, we already now know that the temperature irreversible is hotter than temperature reversible. The final temperature. The initial temperature started was the same. So now we know that the final temperature in reversible case, the gas is more pure. So what about the final pressure? Lower or higher? In case of irreversible. Okay, temperature is higher. Volume is same. Temperature is higher, so the pressure has to be higher. Right? PV is equal to RT. That is all you have to use, nothing more. So if I go back over here, I'll just plot it once more. So if I go back to this diagram, so that's, let me use more area since it's available. So let's say that's the isothermal point and that's the adiabatic point. So we're coming to the same V2, right? We're starting with the same V1. Now that's P2 adiabatic, that's P2 isothermal, that's P1. Isothermal, adiabatic. Okay.
Yes. After expansion, the volume was not.
No. First I said First I asked you the question, what about the volume if the pressures are the same? Second thing I asked, what about the pressures if the volume are the same? All the treatment that we've done for the irreversible case is assuming that we are coming up rather, expanding. We're coming finally to the same volume, right? The pressures are changing. All this mathematical treatment that has been done, see I have marked over here that P2 is not the same as in the reversible case. But the volume is, V2 is. Okay, so we are over here, and where exactly? So, this is my reversible case, right? So that's my adiabat, and again that's my isotherm. And remember, I can always only draw the adiabat when it's a reversible case. I can only draw the isotherm when it's a reversible case, not otherwise. Otherwise, it's only the initial and final points. I don't know what's happening in between. So now, I ask you, the final volume is V2, right? And the final pressure that you have said is less than this, right? And definitely it's more than this because there is a drop in temperature. So it's definitely the pressure of the irreversible adiabatic expansion is more than P2 isothermal, right? Because there's a drop in temperature. Oh, not more, sorry. Less. Going this way, yes. Sorry. Less than P2 isothermal because there's a drop in temperature, but it's more than this. Yes. The temperature of the irreversible expansion is higher than that of reversible, so the pressure is larger than P2 adiabatic, and it's smaller than P2 isotherm. So it lies somewhere in between. So it lies somewhere over here. Let's say. P2 adiabatic irreversible. Maybe I just write here reversible as well. Yes. Now that was a single step irreversible expansion. If I carry out a multi-step irreversible reaction, I would be approaching the reversible case, which means my pressure would decrease further. Right? If I do it more irreversibly, right, then my pressure would increase, go towards the isothermal case. Right? If I do it completely irreversibly, that is against vacuum, then what is the amount of work done? Zero. What is the amount of temperature change in that case? Because dW is 0, du is 0, dt is 0. So in that case, the expansion against vacuum, right, would be identical to the isothermal case. Now, I cannot draw the isotherm, I can only tell you the final points. So, this is one of the questions that was there in Q0, the practice. You had to calculate Q, W, and all these quantities. It's a good thing. You can expand the gas, cool it, basis of a lot of refrigeration, right? That's what your AC does. Okay. So, any questions up to this point? Everything is crystal clear. Great. I love these students. Huh? No, I said give me another couple of lectures, not today. Okay. We need to build the mathematics. By the time we are done with the third law, after that I'll teach you some of this math. But you'll learn on the way. I guess 3 lectures at the most. You'll learn all that later. So everything is clear in this part. Okay. So we have another 20 minutes or so. Let's do some exercises. Okay. Let's do, no, you don't have to get up. Keep sitting and do it. Okay. Let's study some of these thermodynamic cycles because this is what you will be designing, I guess, as chemical engineers. Huh? So let's see some of these thermodynamic cycles. Okay, so the first example that I have over here . So as I said, we'll work with ideal gases in the class. So pressure versus volume. We have an isotherm here, we have an adiabat here, adiabat, isotherm, and then we have another path which connects the isotherm to the adiabat. So let's name this path as A isotherm, then B we have adiabat, and C it's an isochore or just constant volume. Okay, so let's call this P1, P2, P3, V1, V2. Right. Now I've drawn the arrows over here. So we need to go from, sorry? So what we need to do is to, let's say we are at temperature T1 and this is again T1 and that's T2. So we need to go from, one is we take path A, the other one is we first take path B and then take path C. And what we'll do is to calculate a few quantities such as delta U, delta H, Q, W, and I'll introduce another quantity over here, dQ by T. Okay. So all these processes which we are dealing with are one reversible and for ideal gases. Okay. Number of moles are fixed. It's a closed system. Let's do this. So path A. Delta U is great. Uh, delta H 0. Work done. Minus RT log V2 by V1. T is T1, right? Then what else do we need? Q. Minus of this RT log V2 by V1. And dq by t. Wait. R V2 by V1. It's just that it's du minus dw and du is 0. So I get from minus dw. Okay. Let's do the same calculation for path B and C, and then C. Won't need it. Yeah, I mean you can just write it as CP, so don't, or CV. Okay, it's an adiabatic path B, right? Q. W I don't know. Delta U. That's just CV delta T, right? T2 minus T1? T1 minus T2. Great. So delta U is a negative quantity. It's going out from the system. Delta H. It's again an ideal gas. Now I know work. dW is du minus dq. So it's just delta U. And our last quantity, yes, path C, the last one. Yeah, no change in volume, reversible system, W is 0. Delta U would be final minus initial okay. What else are we left with then? Q would be CV T1 minus T2, right? And this fellow? CV ln T1 by T2. बस हो गया. Okay. Now what we need to worry about is to see, as part of this exercise, let's see if what is the path function and what is a state function. Add up all of these. So, Nika, I don't think you'll need a calculator. Whoever was asking for it. So work in path A plus work in path B plus work in path C. What do we get over here? Minus RT log V2 by V1 in case 1, CV T2 minus T1 in case 2, and 0 in case of 3. Right. Minus RT RT1 log V2 by V1 plus, it was a plus sign, right? See, any state function, if I go in a cycle, that means I came back to the initial point. Right? That should be 0. There should be no change in a state function. But this doesn't seem to be 0. Yes?
It's not a cycle.
Ah. What is it then? Okay. Fine. I completely agree, it's not a cycle. What we should do is take path A and in the reverse, and then we get cycle. Right? Or if you want, then what we could do is, instead of doing this way, we compare WA and WB plus WC. Right. If these two come out to be equal, then it's quite possible that it is a state function. If they are not equal, definitely it's a path function. In case of path functions also, sometimes they can come out to be equal, depending on what different paths we have. What was it? T1 minus T2, right? T2 minus T2. Okay. Right. So definitely this is a path function. That's one thing we can say for sure, that yes, it is a path function. Right. You could check out delta U in case of path A is 0, delta U in case of path B plus delta U in case of path C was simply CV T2 minus T1 plus CV T1 minus T2, which also is 0, right? The same you can check with delta H and so on. What I'm trying to introduce now is this function which we have written over here, dq by t, which in case of path A, this was and in case of B plus C, this comes out to be what did you calculate? B was 0 anyway. CV ln T1 by T2, which is equal to R ln V2 by V1 for the ideal gas, right? Huh? Even? Is this an adiabatic problem? Right. So what we get essentially is that this quantity seems to be a state function. See, at least in this case, it doesn't depend on the path. Right? You could try some more cycles and convince yourself that this quantity actually does not depend on the path. I've done something which is implicit over here, and that is that we've used a reversible path. Okay, so it's exactly not this quantity what we are talking of, but it's dq reversible by t what I'm talking of. Okay, this is another state function, and this is something which you already know. It's called entropy. In the next class, I'll go into molecular definition of entropy and try to, give you a feeling of what this entropy exactly is, and then go on to the second round.